Hi, welcome to this presentation on the security model and verified implementation for the IETF QUIC record layer. This is a joint work between Microsoft Research, Carnegie Mellon University, and L'Oréal. In essence, the goal of QUIC is to maximize networking performance by sacrificing the modularity of the current network protocol stack. It achieves this by combining the core features of TCP, like source address validation, fragmentation, acknowledgements, and retransmission, with encryption from transport layer security or TLS. QUIC even includes features found in application protocols, such as multiplexing multiple streams over a single connection from HTTP2. QUIC is the latest step in the quest to lower connection latency. Even the zero round trip or zero RTT mode of TLS 1.3 has a hidden round trip for the TCP CNAC handshake. QUIC is the first truly zero connection latency protocol. But it also comes with other benefits, such as the ability to fine-tune parameters like the retransmission timer or the window size based on application needs. Originally, QUIC was developed by Google as a proprietary protocol to communicate between Chrome and Google services. However, Google QUIC was based on a custom key exchange protocol and suffered a number of critical vulnerabilities. In 2016, the IETF started working on turning QUIC into a standard. So far, 34 drafts have been published by the IETF, and QUIC has seen significant adoption from over 2 million hosts today, according to an ongoing monitoring project by Ruth et al. Interestingly, version turnover is measured at a much faster rate in QUIC than for TLS, and there are also many non-standard versions of QUIC which are found in the wild. When QUIC was proposed to the IETF, a guiding principle for its design was to build it as a wrapper around standard TLS 1.3, such that QUIC would directly benefit from the extensive security analysis done on TLS. However, it soon became clear that the TLS record layer stood in the way of significant optimizations. Hence, the decision was taken to have QUIC interfere directly with the TLS handshake, and the QUIC record layer would manage all data fragmentation and encryption. This raises two problems. First, existing security analysis for TLS applies to the handshake and record layer used together. While many security models modularize the handshake, it is unclear whether it is used by QUIC is safe. For instance, version negotiation, which has historically been a serious weakness in TLS, is replaced by a new negotiation mechanism. The version invariance document of QUIC does not specify a generic defense against downgrade attacks, which is concerning given the diversity and turnover of versions observed on the web. Second, the QUIC record layer itself introduces new cryptographic constructions for packet encryption which clearly require new analysis. We analyze the latter problem in this paper. Early QUIC packets for TLS messages and zero RTT data before the handshake is complete use long headers, but they switch to short headers after the main TLS traffic secret is derived. Multiple QUIC connections can be multiplexed over the same source or destination address ports using connection identifiers. Connection IDs also allow migration of QUIC sessions across network paths. While QUIC packet numbers use 62 bits, sender only send their choice of 8, 16, 24, or 32 of the least significant bits. Furthermore, these bits are also encrypted, which might seem surprising. Normally, the packet number is used to derive the EAD node for decrypting the packets. Leaving the question aside of how packets number are encrypted, it's also interesting to wonder why they would be in the first place. In fact, the QUIC record layer tries to enforce a new privacy property. It should be hard for an adversary to tell if two packets belong to the same QUIC connection. It seems like connection IDs trivially undermine this guarantee, but QUIC actually allows packets to change CID frequently or even in every packet. Therefore, packet numbers become the next best correlator, especially when sending 32 bits on a long-lived connection, hence the need to encrypt them. To create a QUIC packet, we start from a full packet number N and a payload M. The packet number is combined with the static IV to form a nonce used to encrypt M. To protect the integrity of the message headers, It is also included as additional authenticated data for the encryption of M. To avoid sending H in plain text, QUIC's idea is to steal a block of the payload ciphertext C to use as an input to a PRF. This yields a mask, which can be used to encrypt H. However, because H prime must be decrypted before C, it is important that the position of the sample does not depend on ln when H prime and C are concatenated. This is easily achieved by sampling from the end of C. However, QUIC does something different and instead samples after 32 minus ln bits of C. In this paper, we address three classes of security property. First, functional correctness. We provide exhaustive formal specifications of QUIC packet encryption and of the preconditions under which well-encrypted packets successfully decrypt to original payloads. Then we model the cryptographic security of packet stream encryption and reduce it using a formally verified code-based proof to standard PRF and authenticated encryption assumptions. Finally, we present a low-level implementation that extracts to high-performance C code that is probably safe and correct with respect to our formal specification. We start with a specification of QUIC packet formats. For that, we rely on everparse, a library of verified F-star parser combinators that can express secure parsers, that is, parsers for which every valid input has a unique serialization. Although everparse combinators are higher order, their composition only also supports inlining and extraction to highly efficient zero-copy parsers in C. To express QUIC formats, we need to extend everparse with new combinators for bit fields and bit sum types, which capture bit-level dependencies during parsing, such as the most significant bits of flags to indicate long or short headers. At the first lemma, we prove the correctness of the parser assuming the packet recipient knows in advance the length of its own connection ID, an assumption that may look trivial, but in fact rules out some unsafe encoding for connection ID lengths, such as null termination. Then we prove the non-malleability of header encoding, which guarantees uniqueness of representation. Surprisingly, we initially failed to complete this on draft 13 of the standard, because it turned out that earlier draft had a weakness. In the previous versions, the packet number length was encoded as the most two significant bits of the packet number rather than the two least significant bits of the flags. Remarkably, this malleability in the format of short headers leads to an actual attack against the security of packet number encryption using another weakness that we found in earlier draft, which is the ability for a man-in-the-middle attack to alter the server connection ID without being detected by the client. Using this, it's possible to truncate the client's packet number so that the server can still decrypt the packet. While this attack was fixed by the change to short header formats, the problem of unauthenticated connection ID actually proved a lot harder to fix. And it took some 14 drafts to eventually convince IETF that all connection IDs should be authentic. To complete our formal specification, we prove the main correctness of full packet decryption. Not that even legitimately encrypted packets may fail to decrypt if it's received outside the recipient's windows, hence the precondition in the correctness lemma. Again, we also initially failed to prove this lemma because of a mistake in the QUIC specification, allowing an underflow when computing Pn-H. This was fixed in draft 24, and after the fix, we were able to prove the correctness lemma for packet encryption as stated previously. Moving on from correctness, we now try to model the cryptographic security of packets encryption. We follow the Bella-Rogaway methodology of code-based game-playing proofs applied to indistinguishability games where an adversary must guess if it's interacting with a real construction or with its idealized functionality. For instance, a standard definition for authenticated encryption security uses a table indexed by nonce, ciphertext, and header to implement encryption and decryption. We first modify the basic AE definition to account for the fact that the least significant bits of the nonce are no part of the random ciphertext, while the most significant bits NM are an additional input to the decryption oracle used to find the correct nonce in the table. Pushing this definition further, we can return that to a stream of encrypted packets using the states of the decryptor to reconstruct the most significant bits and a counter for generating the nonce. It's worth noting that this definition is specific to the dynamic sliding window method of QUIC for reconstructing packet numbers. Fishlin et al. Have generalized our definition to capture a broader class of validity conditions, which can be expressed modularly from the security of encryption. The main result of our paper is a reduction of QUIC packet number encryption security parameterized by AED scheme and a cipher to standard PRF and AE assumptions over its parameters. While some non-sliding constructions appeared in cryptographic literature, including some variants that are similar to the QUIC construction in a recent paper by Bella et al. At Crypto 19, our result is the first to directly apply to QUIC, and its proof is almost entirely formally verified. To prove this theorem, we fully implement the ideal functionality of non-sliding packet stream encryption based on idealized PRF and authenticated encryption. For instance, packet decryption starts with a lookup in the PRF table over the sample from the ciphertext, and if an entry is found, it is turned into a packet number and nonce reconstructed from the state to look up in the AE idealization table. There is, however, a quirk in the proof. What if two ciphertexts have the same sample? We must exclude such collisions with up-to-bad reasoning, hence the quadratic term in the theorem. Having specified the construction and proven its security and cryptographic safety, the last step is to create a usable implementation. For this, we rely on the verified EverCrypt cryptographic provider, which comes with common specification and verified implementation in C and assembly for most primitives. To use our low-level implementation, we must first allocate the stream states starting from the traffic secret output by the TLS handshake. This step involves multiple key derivations to generate the static IV and AED and cipher keys from the construction. Then the state can be used to encrypt and decrypt full packets, represented by the header and payload. Note that to guarantee that our implementation of packet decryption is constant time, we use abstract types for the length and value of decrypted packet numbers, at least for the purpose of packet number decryption, which proves confidentiality by type parametricity. An interesting technical question is how to relate the low-level implementation to the high-level security model, which of course uses our formal specification at its non-idealized construction. For this, the first step is to preserve the calls to low-level functions, but replace secret arguments with constants. Of course, this breaks functional correctness, so it has to be patched by replacing the return value with the one computed from calling the pure specification, which has no observable side effects. Then calls to the specs can be replaced with calls to the model with idealization turned off, and finally idealization is enabled. On its own, an implementation of QUIC packet encryption has limited value. Therefore, we also implement the rest of the QUIC transports in a subset of Daphne that extracts to C++, and we formally verify that the resulting implementation is memory safe. We plug in the mid-TLS handshake and our verified QUIC trigger layer in order to run benchmark and test interoperability with other implementations. We find that using the Veil implementation of AES and AES GCM, our verified implementation of packet encryption can sustain up to 2 GB per second of QUIC data outputs at the standard MTU of 1,400 bytes. In a more concrete benchmark, testing file transfer through the full application stack of QUIC, we can actually achieve 80 megabytes per second of download output. Although this figure may seem low in comparison to the synthetic test, most of the overheads appears in the Daphne QUIC implementation. And we actually note that even native C implementations of QUIC, such as NC TCP2, do not actually perform much better with 100 megabytes per second at the time of testing. Of course, this was on much older draft of the standard, and we expect more recent versions to perform better. So to conclude, we have formally specified QUIC packet encryption and proved its correctness and cryptographic security. We found several important weaknesses and vulnerabilities in the QUIC standards. We have a fully verified, safe, secure, and correct low-level implementation for packet encryption, and a memory-safe implementation of the rest of QUIC. And of course, all of our code is open source and available on GitHub. Thank you.